Well, hello everybody. Clémence, thank you very much for the kind introduction, and thank you for making an advertisement for the textbook. You will see the cover on my last slide. Just kidding. As you can understand from the introduction, what we are working on is molecules, but I guess most of the things we do you can transfer to the materials world. Well, you will see for yourself. My talk will be about the interactive and automated exploration of reaction mechanisms, and what I basically mean is that you imprint some chemical function of any kind onto a mechanism of elementary steps that we can study with quantum chemical methods. In principle, the idea is very general, although we apply it mostly to catalytic cycles. This is kind of our goal, what we try to achieve, and that is we want to describe complex reaction networks with a multitude of reactants with thermodynamical and kinetical means. And of course, this implies that there is a huge amount of obvious challenges, starting with the construction of structural models, which electronic structure people always kind of ignore. Then there is the problem of the accuracy of the electronic structure model. Then there's some environment, say usually a solvent. You need to be able to get the partition function in condensed phase in order to have access to thermochemical quantities. There's conformational sampling, and so on and so on. So that is, of course, a list of obvious problems. Then I would like to make the point that looking at one single von Oppenheimer surface, doing a simulation on one von Oppenheimer surface, won't be neither feasible nor sensible. You will see why. What we eventually want to do is study concentration fluxes through the network, do real kinetics. And of course, in order to be able to do this, we need to take into account all uncertainties in all quantities, say energies and then of course rates. And so the talks that I'm presenting here will focus on these points. An interactive exploration of structures through ultra-fast quantum chemical calculations, accompanied by an automated exploration, accuracy validation, where we will mostly deal with the reliability of DFT, then kinetic modeling, and finally the generation of accurate reference data in an automated way. Okay? And so the starting point is a chemical problem now. So I just want to sketch to you what kind of problem actually drives us to do these developments, and from there you will see that you can transfer this to similar molecular problems. So imagine that you need to look at thousands of molecular structures at different energy hypersurfaces in order to understand a chemical catalytic cycle. And this is one example. It's an example that we have been working on for more than a decade now, and that is actually the reduction of inert dinitrogen by protons and electrons to ammonia. It's done in industry through the Haber-Bosch process at elevated temperature and pressure. So I think it's 200 bars and 500 degrees centigrade. And nature can do this at ambient conditions in the enzyme nitrogenase. Actually, nobody knows how. The active site is known, but how it is really done, I mean, some people have strong opinions, but I think there is no consensus on how it's really done in nature. And then chemists struggled for a long time to produce a system that can do the same trick as the enzyme. So transforming N2 to ammonia under ambient conditions, ordinary temperature, ordinary pressure. And the first system came out in 2003, and that was proposed by the group of Dick Schrock. It looks like this. It's a single metal center complex here. You see it binds dinitrogen and it has this ligand environment. Then what has been proposed is that you bind dinitrogen and then you start protonating and reducing it. So you need 6 protons, 6 electrons to kick out the first ammonia molecule and finally the second one. Okay, and that is a standard cycle that is assumed to hold true for the system. And now, of course, you can investigate these species quantum chemically, and actually that's what we did some 10 years ago. And it looks like this. So you transfer the first electron and the first proton to the dinitrogen ligand, and actually you can protonate the second nitrogen atom here and then reduce. You can also first reduce and then protonate, and you can even protonate, and that is actually a problematic reaction, protonate the ligand here and reduce and finally end up here, but you will see that the ligand will decompose when you do protonation of the ligand and reduction of the ligand. And actually that's the reason why the system drops dead after about 4 cycles. Okay, so it's a catalytic process, but it's not at all efficient and not competitive. And well, these are the structures you need to inspect for the first electron-proton pair, for the second, third, fourth, fifth, sixth. So pretty many structures. Getting worse because you see this is an optimized structure of the complex. So you see the molybdenum atom here. That's one intermediate. It's the nitrido intermediate. And you see from the top there is actually the acid binding. This is the acid that is used in experiment. You see the proton here. It's about to be transferred to the nitrogen atom. So actually the computational models, the structural models, are much more complex because you need to take into account that your acid and the reductants are reactants that approach the system from one side or the other. Here shown from above. Is that sensible? It is, because also experimentally this structure was found where the base of the acid actually binds to the molybdenum atom. So when you look at the system, it's pretty crowded. You see that you have one reaction channel from above where the reactants can approach the catalytic center, or you have basically a 3,4 degenerate channel B here from below. So there's a multitude of structures that you need to inspect in order to figure out what the system is doing. Now, it drops dead after only a few cycles, and of course you would like to do some design work in order to improve on it. And that's what we also did. So you look at different ligand environments. And of course, for each ligand environment, you need to go through all these steps again. So it's a huge effort. And doing this manually, it's really a pain. And we are still working on this because there are no new suggestions which try to make the ligand more stable so that reduction does not lead to decomposition of the system. Okay, and when you look at the problem, essentially what you find, there are 4 essential steps that you need to be able to accomplish in order to reduce dinitrogen. One of them is, can you bind inert dinitrogen at all? Okay? And then the question is, how would you design a molecular structure that can do the trick? Here we have been looking into inverse approaches. So because we know what we want to do, and now the question is, what is the molecular structure that can do the trick? Rather than doing high throughput screening, we were looking into concepts that allow us eventually to find molecular scaffolds that sustain some certain molecular structure that we understand need to be part of the cycle. To give you an example, say you start from a chemical fragment, and we call this gradient-driven molecule construction. Where we start from a fragment, say this is a metal atom, and it can be a metal of your choice. Could be molybdenum, for instance. There's a dinitrogen ligand. And you could ask, well, let me bind dinitrogen to this atom. So what kind of environment do I need in order to make this a stable subsystem in my huge molecule? And of course, you want to have the binding energy sufficiently large. What you also want to do is you want to achieve that all forces on all the atoms basically vanish. And so that's kind of the scoring function for the search of molecular scaffolds. That's something that we implemented in an automated way, and we can now search chemical space for scaffolds that support the stabilization of a certain molecular fragment. Let me go back one slide. I mean, you could also ask the question, well, I not only want to have the dinitrogen ligand binding to the metal center, I also want to have it activated. Usually it means that you have an electron transfer onto the N2 ligand, and qualitatively speaking, that means you occupy an anti-bonding orbital, which elongates the bond such that you produce a diazinoid structure, and that will also then distort. So you will have an angle. So you could just elongate the distance between the 2 nitrogen atoms here and create an angle of, say, 120 degrees, and then say, well, I want this fragment to be stabilized. And then you go through the whole design process again and try to find a scaffold that can support that structure. So with this tool, we have a tool in our hands which allows us to explore chemical space. But in general, the problem is that, of course, chemical space is just huge, and you need to do something about it in order to efficiently screen it. And our credo here is that we believe in a combination of interactive and automated exploration. So we think that with the human eye, with some chemical and physical understanding, it's easy to spot wrong directions of an automated exploration. So that's why we think we need both. Both kinds of exploration, I will give you all the details on the slides to come, store their data into a reaction network. And that reaction network basically maps out all the understanding that you have of a certain chemical process. And of course, you would like to understand how accurate the data that you're storing actually is. And so we have automated benchmarking and refinement steps for the network until we reach a point where we can do kinetic modeling. And let me walk you through the different steps. And I start with interactive exploration. So for a couple of years, we looked into something that we call real-time quantum chemistry. These days, you can do quantum chemical calculations real fast. If you consider the catalytic cycle that I've introduced you to, then most of the chemical processes just require you 100 to 200 atoms to describe the essence of the system. The rest you can embed using some suitable embedding theory. So say with 100, 200 atoms, you can do a lot of chemistry. And for 100, 200 atoms, you can carry out calculations real fast. So fast that you immediately receive the data. So say you're manipulating a structure and the result is there like this. So how do you deal with the information flow? One of our solutions is we look for new hardware devices, like these force feedback devices, which you might have seen before. It's a force feedback pointer device where you basically hold a pen, and the pen is connected to some electrical to some electrical engines, and the pen is an input device, but at the same time also an output device. So you have basically 6-dimensional input and 3-dimensional output, which allows us to grab an atom, move the atom around. Now the quantum chemical calculations are ultra fast, so the results are there instantaneously. And you manipulate the structure, and the whole rest of the structure can, first of all, relax, and also the quantum mechanical forces that you evaluate for the atom that you grabbed are transmitted back to the machine. So you feel the force on your atom, calculated in real time. And that actually allows you to explore a potential energy surface. So the force here is a descriptor to understand what kind of path I'm taking to explore a Born-Oppenheimer potential energy surface. So imagine that you're looking for transition states. That means you somehow need to walk uphill to figure out where the saddle point is, the transition barrier. And the force will allow you to do that. We have implemented this for interactive reactivity studies as an API to the Samson editor, which is actually developed by a group in Grenoble. And so you can, in this molecule editor, you can load in our program and do the exploration. So you see an example, this is actually a screenshot. That's a molecule, an organic system, which undergoes 3 consecutive electrocyclic reactions that you can study in real time. That's one of our demonstration examples. And all the stationary points that you encounter, they are stored into a reaction network automatically, so that you can go back to the structures that you visited. It's basically a way to do some really quick exploration. You see, this is the energy that you see, and of course it's not smooth, right? Because you do manual exploration, and you can't expect that this is a smooth energy curve. But it's a starting point for an automatic search for minimum energy passes. So the whole interactive system here allows you to do some exploration where all the hard work is then not done manually but automated, in an automated way in the background. And actually we're working on a new graphical user interface that makes this handling much easier. Because the point is, this Samson editor is that's a great tool, but it looks like it has kind of an office surface. So you need a course in order to understand what all the buttons do. Right? And I think this is not necessary. You just want to talk to your molecule, and so you can have an editor which is context dependent. Only when the computer program thinks that you need to interfere with what is currently being done by the computer, then you see a menu, otherwise you don't. There are a couple, one ingredient is of course that you can do the calculations in an ultra fast way. There are more issues. All the orbitals are optimized self-consistently. Now you create structures manually which are so far away from the minimum structures that orbital convergence can be an issue. So orbital convergence can be really a pain in the ass, and of course you can improve on it by special techniques, extrapolation techniques, and we did this. But this problem will not go away. It has also been seen in the group of Todd Martinez, who has a year ago 18 months ago, published a paper on steered first principles molecular dynamics, where they use, you see the same device here, where they use the device in a molecular dynamics context to introduce a force into the dynamic simulation. Okay? And then this is first principles molecular dynamics, and then they see, of course, the same problem that we have seen before, where for strongly distorted geometries, however, hundreds of SCF iterations are sometimes required. Even worse, the SCF calculations may diverge, causing the entire calculation to abort. Unacceptable, of course. This is a huge problem. For pathologically long MD steps, such as those requiring many DIIS iterations, the display trajectory is frozen and haptic input ignored until the MD step completes. The problem when you do this, the problem is that the immersion of yourself into the problem is broken. Because you're holding the pen, nothing is going to happen because you're waiting the computer to complete the task. And that is really a problem when you use this setting. And so we came up with a solution which we call a mediator strategy. So what we do is we calculate the forces from a surrogate potential, where the surrogate potential is always a quadratic approximation to the real surface. And this quadratic approximation ensures that, say, if it takes longer to converge the orbitals, then the parabolic potential makes sure that you don't leave the trusted region. Okay? And then nothing stops and the immersion is still there. Works pretty fine. Problem here is that the haptic force feedback is on a kilohertz frequency. That means that you need to finish the quantum chemical calculations on a millisecond time scale. With certain tricks like this one, you can do it in 100 milliseconds, and that's fine. But every 100 milliseconds, you need an energy and a gradient. So you need to converge the SCF iterations. It's a much more strict constraint than for visual feedback, where you have 60 hertz. Okay? But this works pretty nicely. Now, so you have this tool where you get this immediate feedback. You see your results immediately. But what you do is you explore one Oppenheimer surface. So you're exploring a molecular structure where you made a choice what the charge in the system is and also the spin state. And now it could be that what you're looking at is actually not what you should be looking at. But nobody will tell you. But the computer can do because the calculations are so fast. So what we're actually doing is we run various calculations in parallel in the background for other spin states, other charges, or protonated species to figure out whether these processes can be competitive, so that you understand that there could be some interesting chemistry going on which is worth exploring. And we call this general concept molecular propensity, and there's one example here. It's shown for a prototypical system which has been studied experimentally in the mass spectrometer some 15 years ago. And you see it's an iron oxide, a cation, which reacts with molecular dihydrogen to produce the iron, cation, and water. The problem is that when this was measured, it was difficult to explain kinetically what was going on. And people figured out, that was Sazon Scheik, Helmut Schwarz, Detlef Schröder, that the only way to understand the kinetics here is to assume something which they then coined two-state reactivity, where you start from a sextet spin state, and in between you switch to a quartet surface, because on the sextet surface the barrier is so high that you wouldn't see the reaction, but the reaction was observed. The quartet surface comes down in energy, the system switches to the quartet surface and back to the sextet surface. And this is the only way to explain the kinetics. And when you do this now in our setting, in our real-time setting, you see here this is iron, that's oxygen. You see the two hydrogen atoms already binding to the iron center. And when you approach this structure here, the computer tells you that this is the quartet state coming down. So you would have seen this in our setting. And it's a tool to really find things which you didn't expect to happen. And then it goes back to the sextet surface. Of course, you need to tell the computer that you actually would like to explore the quartet state. So it will stay on the sextet surface, and you let the computer store the information, and you can go back to that point and then later explore the quartet surface. This is an example for the Schrock system. You see the molybdenum center here. We have simplified the ligand here, the environment. You see this is a dinitrogen ligand carrying already two hydrogen atoms. There's an acid here, and you look at a proton transfer to the nitrogen atom here to produce the first ammonia molecule. Now when you do that, this is what you observe in the real-time setting. Right? This is the The red curve here, the energy goes up much too high, so it's in kcal per mole. It doesn't look feasible. But at the same time, the computer is doing a calculation for a reduced species. And that calculation for the structures that you're exploring is given here in blue. And you see, at some point here, there's obviously a proton-coupled electron transfer step, which makes the whole thing energetically feasible. I should say, you see it's written here, exploration coordinate. It runs from 0 to 5. That's actually in seconds. So you see this immediately. And complementary to this, what we do is automated exploration. Because for sure, you can't look into all structural details manually, and you need some automated exploration. And since computer time is cheap and DFT calculations are cheap too, we actually would like to do massive searching, even if at the danger of wasting computer time. It's a big data problem because you can't look into all the results. You need to have algorithms doing that for you. And so we worked on an automated evaluation of and data representation techniques. I will give you an example in a minute. Let me just briefly mention that such techniques are being developed in many groups around the world currently. In chemistry, very popular, the work by Maeda and Morokuma has attracted a lot of attention because they have discovered a lot of new chemistry, important chemistry, with methods that they call artificial force-induced reaction method, or AFIR. And of course, in molecular dynamics, there's a much longer history of doing this. And in quantum chemistry, recently, people also looked in heuristics-guided exploration. A lot of work has been done in the context of organic chemistry, which is based on molecular graphs and pretty much tailored for organic chemistry. But since we do a lot of inorganic chemistry, we can't use this. And we also work on heuristics-guided exploration, but with reactivity descriptors taken from quantum mechanics. So where the principles are more general. What do I mean by this? Well, let's go back to the Schrock system. You see two Schrock complexes here. This is the original one, the nitrogen binding one, in the small model. This is the intermediate, the nitrido intermediate, where the first ammonia molecule was split off. And what you see here is the electron localization function. It basically is a measure to tell you where you would protonate. And when you inspect this function, you come up with these reactive sites marked in red here, where you could add a proton. And we are very conservative. So we better add more of these reactive sites to see where the proton could go in order to not miss any important intermediate. And so you end up looking at 10,000 intermediates of the whole cycle and at least 1,000 transition states. Okay? And we can do this in an automated way. And even the evaluation is done automatically using Python scripts, and this is the result. So basically you see here, this is again, the cycle is the catalytic cycle that you have seen before. Every line here basically marks one Born-Oppenheimer surface, and on that Born-Oppenheimer surface, the exploration has identified various stable intermediates, all connected by elementary reaction steps, and they color coding assigns an energy to the intermediates. And each of these figures has been produced automatically by the scripts. And now you can inspect of course, every circle corresponds to a structure, and now you can inspect all the relevant structures of relevant energy in order to figure out what's the chemistry, what the implication for the chemistry is. And this is the result. So again, you see our catalytic cycle in the center, but now we realize that there are other reaction pathways that are feasible under catalytic conditions. Like this one, and you see here in yellow, that's where the proton goes. Or this one here. So the simplified cycle is not at all a good representation of the catalytic cycle. And what we still miss here are decomposition reactions. So the full picture will be even more complicated than what you see here. Of course, the next step is you can do kinetic modeling. And of course, we have the transition states for the process too. We basically automatically localized around 300 relevant transition states. Kinetic modeling is also not easy. What is mostly done is working with some sort of master equations which generally restrict the kinetic to first order kinetics. But that's a limitation that is not working for us. So we at least need to be able to model bimolecular reactions. And so we implemented a scheme that we are currently testing whether it can be applied under all circumstances, and that is based on computational singular perturbation. I think I skipped the details here. You might want to look it up in the recent Faraday discussion paper of our group. But so if you do the kinetic modeling, then at some point, energy barriers enter rate expressions. And the energy enters an exponential. So any error that you have on the relative energy will have dramatic consequences on the kinetic modeling. So what about accuracy here? And all the results you have seen so far are basically DFT results. I would say, I don't know whether you agree, that it's a little hard to really assess how accurate DFT really is, at least in the field of inorganic chemistry, coordination chemistry, because it's hard to get reliable reference data from calculations, because you need very sophisticated ab initio methods, and well, sometimes they work, sometimes they don't. So what we had done here is we picked experimental data. These are experimental binding energies for reactions with transition metal complexes, 10 in total, which were measured by our colleague Peter Chen at ETH. And the binding energies in a mass spectrometer, so it's a perfect setting for us. We can look at the isolated structures, no surrounding, and so on, makes it easy for us. And they can do the measurement such that they extrapolate to 0 Kelvin. So all we need to do is subtract the 0-point vibrational energy. And then we can directly compare to the measured data. Now when we do this for standard functionals, as you can see here on the right, this is what we get. And you see this is now in kilojoules per mole, and you get a scatter of plus minus 50 kilojoules per mole. Okay, so the spread here is 25 kcal per mole. It's huge. And we have some we see some difficulties here with dispersion corrector functions, which we actually don't understand. But the point is, even if we ignore these, we see that there is this huge spread of 25 kcal per mole. And of course, we were not the first to see this. Right? When you look into this review by Cohen, Moritz Sanchez, and Yang, published in 2012, Chemical Reviews, you see similar pictures here. Here you have the list of standard functionals, and then the plotted is an error here. And you see the error bar is of the same size. Even if you, and that's important, even if you look at systems which are similar, so say one complex at different stages during a reaction, and this example here are hydrogenase model clusters with 2 iron centers. You get a spread of, say, 20 kcal per mole. I mean, when you look at the figure, you think the spread is even larger, but there are a couple of unreasonable functionals nobody would use, like this MO6HF. But if you pick the reasonable functionals, you still have a spread of 20 kcal per mole. And when you further look into the literature, you see that you have large mean absolute errors for benchmark sets. Well, what does it mean for transferability? How much can you trust your DFT calculation if you see these huge errors? In organic chemistry, often you see smaller errors, but as soon as you have 3D transition metals, it's really a pain. And for predictive work, really not acceptable. In order to better understand this, we asked, can we at least know how wrong DFT is likely to be for the specific case that we are inspecting? And here we built upon an idea that was published in 2005 by Cessna and co-workers, who worked on sloppy models, and in 2005 the ideas they were elaborating, they transferred to density functional theory. And the idea is to map the real error to a sampling error of a class of density functionals. Yeah, Cessna, Nørskov, Jacobsen, they have come up in the meantime with functionals that do this. They probably you've seen it. I don't know whether it's in Quantum Espresso. Do you have it?
No, but we interact quite a lot with Karsten and Thomas and the Nørskov group.
Okay, I think it's implemented in WASP, but not that much used.
In GPO also, they're coded.
And so I don't know why, so I've just an idea why this is the case. The point is that it's, say, 5 to 10 times more expensive compared to a standard functional. But say if you use beef van der Waals, you see that the mean absolute deviation is still 60 kilojoules per mole. If you use a more recent functional like mbeef, it's still 34 kilojoules per mole, which is basically the accuracy you get with PBE, I guess. So it's just an idea. I think it's more expensive and you don't gain much in, in, in accuracy. So for our purposes, kinetic modeling, these these mean absolute deviations, and this is for the training set, right? They're just too large. So what we thought that we should do is something that DFT people would say you should never do. We do parameterization for a tailored benchmark set. So we basically, this is then a semi-empirical method. We use a functional that is parameterized for our problem in order to get the error bars down. And actually, I don't care. As long as I know how wrong I am, this semi-empirical method is fine for me. What we also do is we use a range-separated hybrid functional because we think that these functions are most accurate, at least for molecular purposes. So that's something that we picked for our parameterization. And then in the end, we get an error estimate with a standard deviation and so on. We used actually the LCPB0 functional, and we optimized the parameters in the functional. And in order to indicate this, we put a star here. Okay. Of course, we need reference data. Again, you see this is the toy model. Again, Schrock catalysis. We calculated coupled cluster reference data for the system. Basically, reaction energies and barrier heights. And parameterized our functional for it. This is what we get. You see the largest absolute deviation, mean absolute deviation, standard functionals here. This is our reparameterized functional. And you see it's doing fine, but not as good as one would expect. So what we see is that there's still inflexibility in the functional. We need to have a much more flexible functional in order to get this mean absolute deviation further down. This is now in kilojoules per mole. That is our data set here of reaction energies and barrier heights, and you see our data points in black with an assigned error bar, and compared to also results that we get with standard functionals. And now what you would expect here is that the error bar that is predicted has something to do with the real error. The real error is always the deviation of the black point from the zero line. And in most cases, you see that the zero line is within the error bar, but there are some cases like this one here where this is not the case. That is also a sign that the functional is not flexible enough. So we need a much more flexible functional in order to do this error estimation here. But say we work with the data, now we can attach error bars to our reaction energies. Again, you see the Schrock cycle. Now I have numbered all the reactions, R1 to R10. You see these are now electronic energy differences, and there's a standard deviation attached to it. And the interesting thing is, for similar reactions, you get different standard deviations. Okay, the error is different for different reactions. Okay, say you want to do this. How can you make sure that for any kind of system that in the future you intend to study, you get really reliable reference data? Well, one thing you could do is explicitly correlated coupled cluster calculations. But that is probably only you can only trust this if this is really a single reference case. So if you have a strongly correlated molecule, then it's not clear whether you get really accurate data from such a calculation. And so what we have been working on is actually a multi-configuration approach based on density matrix renormalization group. DMRG is a technique that was proposed for linear spin chains in the early 90s by White and has entered quantum chemistry in the late 90s, and there's been a lot of development in the last 15 years, and now it has become a standard method, which is pretty remarkable because quantum chemical approaches like configuration interaction or coupled cluster, they have a long tradition, decades old, and it's really hard to compete with them. And DMRG managed to do that within the last 10-15 years. It has become now really a reference benchmark method. But we want to do it in a black box manner because we need reference data, and you can't, I mean, it's not feasible to have always asked an expert to produce a reference data. It must be done automatically in order to do the parameterization of the functional, right? How can that be done? I'll come back to this in a second, but before I would like to emphasize that before 2007, people even believed that DMRG can't be used for transition metal systems at all. Because people thought DMRG was developed for spin chains, and you can show that it works remarkably well for linear spin chains, but not for sheets of interacting spins. Okay, so why would it work for a compact, strongly correlated transition metal system? And actually, people thought that it's not possible at all, and our point was, well, if it is at least better than what we have available with other traditional methods, then it's useful for us. And that's actually something that we showed in 2008, and since that time, many people have looked into transition metal systems. And it has become evident that DMRG is the method to go for complicated transition metal systems. We have a new implementation of DMRG solidly based on matrix product states and matrix products operators. These things refer to the representation of the wave function. Basically, what we usually have is an electronic wave function given here, right, where you expand in a set of Slater determinants. This is now written as an occupation number vector, but never mind. So you have a typical CI type expansion here, and now what DMRG does is it optimizes actually such a complicated representation of a CI coefficient, and that is a matrix product state. Okay, and you have a similar representation for all the operators. Say, for instance, for the Hamiltonian given here. Our implementation is based on the code for spin Hamiltonians developed in the group of Matthias Streuer, and of course we have full spin adaptation and so on. It's a pretty efficient code. You can get it for free from our webpage. Now, so our choice for the reference data is multi-configuration self-consistent field based on DMRG. But this is no black box, because you need to pick orbitals in which you construct your many electron wave function. That is usually in quantum chemistry called the choice of the active orbital space. Yeah, and then when you do that, you do the construction of the wave function in a limited orbital space. You neglect, of course, orbitals which are important for getting quantitative accuracy. And what you lack then is what we call dynamical correlation, and you need to capture this in a subsequent step somehow. So let's see how that can be done. First of all, DMRG has a couple of advantages which actually allows you to do the orbital selection in an automated way. I mean, when you do DFT calculations, you are not at all concerned with this. But when you do wave function theory, then this is a huge issue. Usually it requires a lot of experience, and that is actually not a good situation in science where you need an expert to tell you what kind of orbitals to pick. You need an objective criterion to do that. And DMRG can do that for you because DMRG is iterative. That means you can stop at a point where, say, the energy is not yet converged, but the qualitative nature of the wave function is. Okay, and that means you can do a quick and dirty, cheap DMRG calculation for a really large active space, because DMRG can do that. The standard size of orbital spaces in these theories is about 18 orbitals. So in a standard approach, you can pick 18 orbitals, and then there is an exponentially scaling wall which does not allow you to pick 19. Okay? DMRG can go to up to 100 orbitals. So you can pick a large active space and figure out what are the essential orbitals that you should have picked, and then you do the calculation with those orbitals. But of course you need a selection criterion for this, and what we use are measures from quantum information theories that are evaluated for grand canonical reduced density matrices. These are, in the extreme, these are density matrices defined for one orbital. And for a single orbital, the dimension of these reduced density matrices is 4, because you have 4 states for a spatial orbital, which means unoccupied, doubly occupied, spin up, spin down. Okay? And so the dimension is 4. You can diagonalize the matrix, and then you get eigenvalues. These are the omegas here, and you can sum over this Shannon type expression of all the eigenvalues and get a quantity which is called the single orbital entropy. You can do that also for 2 orbitals. For 2 orbitals, you have in total 16 states, and that means you have a dimension of that density matrix which is 16 by 16, and you get 16 eigenvalues, and you do this calculation. And of course, when you do it for 2 orbitals, the single orbital entropy is kind of hidden in there, and so there is duplicate information. You go on and define something that is called mutual information, where you subtract the single orbital entropies from the 2 orbital entropy. Okay? And these are the measures from quantum information theory that allow us to assess correlation in the orbitals. What people usually do is they use natural occupation numbers, but natural occupation numbers are either close to 2 or close to 0. And now when you have a strongly correlated system, then you have many of the orbitals close to 2 and many which are close to 0, but not exactly 0 or not exactly 2. So which one do you pick? These measures show a larger spread. And you have even the possibility to renormalize the measures to your molecular system that you're looking at. So that's why we pick these measures. And the explicit values don't matter. What matters is how the entanglement looks like when plotted graphically. So what we do is we put all the orbitals on a circle, so all the numbers represent an orbital, and then the single orbital entropy is given here. The size of the single orbital entropy is given by the area in red here of the circle, and the mutual information is given by, is encoded in the thickness of the lines connecting always two orbitals. And we call these entanglement diagrams. Here you see explicit calculations for really challenging systems. The permanganate anion and the porphyrin system here. You see here we can even plot the orbitals. You see we have 25 orbitals here, but here it's already 67, if I'm not mistaken. What this picture should show you is this is a fully converged DMRG calculation, and this is one of the quick and dirty calculations. So this one is fast. It basically takes you a day. But since you don't need to invest any time, who cares? Okay? You invest a day, you get this picture, and it allows you to pick those orbitals which are highly entangled. Those are the orbitals that you should have in your active space. And you can identify them immediately by just looking at the single orbital entropy. Okay? Because those with a low value you would ignore. When you do that, you figure out that the active space that you would pick is also the active space that the expert would have picked. So that is actually doing what you want to do. And you can do it automatically, and this algorithm should just show or emphasize that it can be done automatically. You don't need to take care of it. Now, does it work? Yes, it does. Let me show you one famous example in chemistry. This is called the Cu2O22 plus torture track. That is this tetraatomic molecule is basically the core of an enzyme. And so you have the two copper centers here, and they are bridged by oxygen. If you have this situation, then it's a mu-oxo bridging mode, and that is basically what you see, the structure that you have here on the left-hand side, and on the right-hand side, you have a chemical structure where the oxygens are closer, such that they, as a chemist, you would say there's a bond, and it's a pair oxo-ligand that is coordinating. So chemistry-wise, these are two different species. Now, Chris Kramer and co-workers in 2006 did a traditional CAS-SCF calculation and realized that they got results which were totally wrong compared to completely renormalized coupled cluster data. And that is this one here. Okay, it's all in kcal per mole, and you see the red curve is totally off. So traditional multi-configuration SCF is not working here. And it all has to do with the fact that this active space that traditionally you can afford is just too small. Now, we approach this automatically. We pick all relevant valence orbitals, and we do a quick and dirty DMRG calculation with 48 electrons in 36 orbitals. And you get this result. And it's obviously, it's completely crap. But it's a quick and dirty DMRG calculation which solely serves the purpose to pick the orbitals. Once we have picked the orbitals, we do a clean DMRG calculation, and it turned out that we need to pick 32 electrons in 28 orbitals, and we get this black curve over here. And you see it's fine. It does not match the reference, and why is that? Because we still lack dynamic correlation. We have thrown away a couple of orbitals, which we shouldn't have done. So we have a proper behavior of the curve and still a deviation which is due to dynamic correlation. How do we get the dynamic correlation? Well, there are various methods. One is multi-reference perturbation theory, but another one which looks promising is called short-range DFT, and that will be my last example. Let's first look into the multi-reference perturbation theory. This is a hot topic in DMRG applied to quantum chemical problems. Many groups are working on this. And I think in Journal of Chemical Theory and Computation, you'll find at least 10 papers last year on the problem. Because for the multi-reference perturbation theory, suddenly you need 3 and 4 particle reduced density matrices, and they break your neck. They are a pain in the ass. So DMRG is a nice method, and all the advantages are gone the moment you switch on a standard multi-reference perturbation theory. And so people are trying to find a way to define a multi-reference perturbation theory that does not break the efficiency advantages of DMRG. We have done this too, and this is a calculation which should just show you that we can do these calculations for transition metal systems. It's actually a system that is turned out to be a problematic system, because you see it's a cobalt complex where actually the 2 nitrogen atoms here and there are bridged by methylene bridges of different element size. So the smallest one is one where n equals 3, and then for n equals 3 it wasn't clear what the what kind of spin ground state was a true ground state, whereas for n equals 4 to 6, it was clear it's diamagnetic, and so meaning not magnetic at all. And so in reference 5, published in 2015 in Inorganic Chemistry, people argued based on DFT and new experimental results that this system for n equals 3 is actually diamagnetic. So let's see what we get with ab initio data here. You see, these are the DFT results that were obtained for the gap between the singlet and triplet states in electron volts, and it ranges from 0.45 to 1.09. We do a DMRG SCF calculation with the settings that you have seen before. We get 1.67, then we add dynamical correlation. It's with DMRG NeFPT2, that's a specific multi-reference perturbation theory with nice formal properties. We get 1.52, and the difference is not large, which basically tells you that dynamic correlation is not that large in this system. So this works. It's for an active space with 22 electrons in 22 orbitals and more than 1,000 basis functions. This is my last slide. You can also include dynamic correlations through short-range DFT. So you do a range separation of the electron-electron interaction. And the long-range part you describe with a wave function method, DMRG. And the short-range part, which is responsible for the dynamic correlation, you do by DFT. This way, when you start the DMRG calculation, all the dynamic correlation, almost all the dynamic correlation, is already in your orbitals. Okay? And it has a nice effect on the active space, because all the electron correlation in the active space is also regularized. So let me show you what I mean. We pick one example from our reference set, which has been measured by Peter Chen. You see, this is a ligand which is abstracted from a kappa center. Experiment tells us that the binding energy here is 227 kilojoules per mole. Now, when we do a DMRG calculation, actually, you see 3 of them here, 10 electrons in 10 orbitals, 20 electrons in 18, 30 electrons in 22 orbitals. You see that the binding energy changes from 133 to 174. So first of all, you note that there's a pretty large change, which is actually something you don't want to see, and the difference to the reference is huge. Now you switch on short-range PBE, and suddenly you see it's 217 to 225. So at once, you're in the right ballpark. And also, the spread is much smaller, which is an indication that the active space is regularized. So you change the size of the active space, and the result that you get does not depend a lot on it. So this is why we think this is a promising method, especially since the cost is dominated by DMRG and not by a step which is coming after DMRG. Brings me to my conclusions. So you've seen that transition metal catalyzed reactions are enormously complex. And in order to do a complete exploration of what these systems are capable of doing, if you really wanted to look into a new system for truly predictive work, you need to have new tools. And we believe that these new tools are suitable for the purpose. We have interactive real-time quantum chemistry. We have massive automated search for elementary reaction steps, kinetic modeling that works for different timescales up to bimolecular reactions. We have error estimation for DFT results and rigorous automatized benchmarking with black box DMRG, all in place now. The work was done by all the people in my group. You've seen the names in the references that were on the slides, and I'm very grateful to the work that they are doing. Financial support came from ETH, the Swiss National Science Foundation, the German Fonds der Chemischen Industrie, the Danish Willem Foundation, the Austrian National Science Foundation, and that brings me to my end. Thank you very much for your kind attention. And by the way, this is a textbook. Thank you.